How are you? I hope you will be fine. So, up till now, we have been studied the Laplace equation and its solution in one variable, in one dimension, in first coordinates of rectangular components and spherical coordinates. And we have also studied the Laplace equation in spherical coordinates in two dimensions. And today we are going to discuss the Laplace equation solution in cylindrical coordinates and its cylindrical harmonics. It's very interesting that Laplace equation has solutions in different coordinate systems. And in cylindrical coordinate systems, we know that there are three parameters, three coordinates r, theta and z. And in this topic, today we will deal only with r and theta, not with z. Because we are going to restrict ourselves on first two coordinates. And for cylindrical coordinates, the solutions are appropriate for certain problems involving a long straight cylinder or wire. But are not appropriate for those dealing with short cylindrical segments. Means these solutions that we are going to deal today are only applicable, appropriate in long cylinder, not in short cylinder, or in long wire, not a smaller segment. Let's suppose if this is cylinder or this is a wire, if it has significant length, then these solutions are appropriate for application point of view. If potential is independent of z, as I have told you that we are dealing only with the first two coordinates and the third one is z. We are not going to involve the z in our discussion. And if the potential, what is the potential? The variable in the Laplace equation. We know that Laplace equation at d square phi over d r square is equal to 0, and this phi is basically potential. And potential is the function of two variables, two coordinates r and theta, but z is not present there. It is independent of z. The Laplace equation in cylindrical coordinates will become 1 over r partial by partial r into r partial phi by partial r plus 1 over r square partial square phi by partial theta square is equal to 0. This will be the Laplace equation in cylindrical coordinates. R is the first coordinate of the cylindrical coordinates and theta is the second one. Now we will use the separation of variable method. We have studied in mathematical methods or mathematical physics and quantum mechanics as well, a very famous method to separate two variables that are involved in a single equation. We use the method of separation of variables. Because in this equation, r is also present and theta is also present in the single equation. Here you can see r and theta. You cannot solve it because two variables, two coordinates are in the first term, in the one term. You will have to separate r and theta. For separation of r and theta, you use the separation of variable method. And this separation of variable method, let's suppose if phi is equal to y of r and multiplied by s of theta, means this phi potential is equal to y multiplied by s. Y is the function of r, first coordinate, and s is a function of theta, second coordinate. Means this phi, you have separated it into two parts. First is y, second is s. Y is the function of r, s is the function of theta. Instead of phi, you will put value phi is equal to s into theta in this equation. And also you will multiply this equation with r square. And by multiplying with the r square, this r square will be diminished, eliminated from this part. And by multiplying r square over here, this r will be finished. Only one r will be left over here. And we afford r in the first term because we want to make it sure that the first part of this equation only depends upon r, the first coordinate. And in the second term, we don't need the r, we need only theta. And we don't need theta over here. So if you will multiply with r square, the equation thoroughly, you will get away from this r in the second term. Okay? We'll multiply and put phi is equal to s theta. If you put phi, this phi is equal to s, y and s theta, then y is the function of r and the derivative is with respect to r. So y will always be within the derivative and s is the function of theta. And if you put here y into s, then s will be treated as constant. Because our derivative is with respect to r and s is the function of theta. Therefore, s will be treated as constant and will be taken out of the derivative. You understand my point? So, after putting phi is equal to y into s theta, over here, only we will write dy by dr. This term, s will be out of it. No, it will not be equal to 0. The sum will be equal to 0. S of theta will be out of this. Actually, I have simplified the three steps into one step. S will be here, then s will be on the second side and will be divided on the second side, because you will take it on the right hand side, this term. On the right hand side, it will become minus 1 over r square partial phi square by partial theta square, and then you will put this value in the equation, and s of theta will be multiplied over here, and on the second side it will be divided, and you can see over here on the second side, on the right hand side, it is being divided. You did not get my point.
दो चीजें जब आपस में जमा हो रही है ना, उस साइड पर जाएगी नेगेटिव हो जाएगी.
Yes, okay. This is negative over here.
रिलेशन तो वही रहेगा ना पॉजिटिव नेगेटिव का. तो फिर हम कैसे डिवाइड कर सकते हैं अंदर जाके?
No, the total sum of two terms is equal to 0. Okay, let's pause. Let me do it over here. 1 over r partial by partial r into r partial phi by partial r is equal to minus 1 over r square partial square phi by partial theta square. Okay, you can write this term like this one. You just multiply with r square. If you multiply with r square and r square over here, these two will be cancelled out and only one r will be left over here. And after that, you put here, instead of r partial by partial r into r partial y function of r and s function of theta over partial by partial r is equal to minus partial square y of r s of theta over partial theta square. So you can see that
constant होगा
yes, this is the partial. S of theta will be out of here. S R partial by partial R into we will have R y of theta over partial by partial R is equal to minus y of R will be out of this derivative because it depending upon the theta. Derivative is with respect to theta, then y will be treated as constant. You will take out of this derivative, you will have yes, this partial square s of theta over partial theta square. Okay? Now this s
y of r I y of theta है इधर.
sorry,
इधर लेफ्ट साइड पे.
this one
y of theta आएगा, y of r आएगा.
sorry, y of r, not y of theta, y of r. So this as function of theta will be taken to this side, it is being multiplied over here, on this side it will be divided. So you will write it as r partial by partial r into r y of r over partial by partial over respect to r derivative minus y over s function of r partial square s of theta by partial theta square.
इधर हम s of theta नहीं लेंगे. इधर s of theta है उसके साथ.
Okay, fine now, no problem. It is understood that s is the function of theta. I did not write the theta deliberately because we know it is the function of theta, and this equation is over here. I told you that I've written the simplification form of the equation. After performing 2 to 3 steps, you can get. I'm telling you about the k. You are going to ask the question of k.
तो सर y of r का मतलब लेके हैं, इसका मतलब ये इधर से राइट साइड से मतलब जाके डिवाइड कर दिया.
Yes, that this y of r is being multiplied over here. In this side, it will be divided. It is parental over here, and we understand that it is a function of r. If you write as a function of r, very good. Otherwise, it is understood that it is the function of r. Okay. After that, by putting this separation of variable method, you got my point? Okay. Then you make the both sides equal to a one constant. In the separation of variable method, you can write the both sides equal to a one term, because if this is equal to 5, this can be equal to 5 because both are equal. Let's suppose there is no k. This is equal to this one, and if this is equal to k, this will also be equal to k. That's why I have written over k as a separation constant. K is a separation constant. The theta equation is particularly simple. This one, look, 1 over s d square s over d theta square. It's very simple, is equal to k. Then if s is equal to k, you can simplify this term. Use only this term. I just write over here for your understanding that if this term d square s by d theta square is equal to minus ks, we can write it as like this one, and it is a very simple very simple ordinary differential equation, and solution of this equation is very simple and is cos a power 1 by 2 theta. If you solve this differential equation, and I hope you have done the differential equation course in your previous classes, and you can solve it by integrating on both sides. first is integration and second integration, you will get the value of this s is equal to cos k theta, k power 1 by 2 theta, and sin k power 1 by 2 theta. Each must be a single valued function of theta. Therefore, you can write for this solution cos k power 1 by 2 into theta plus 2 pi is equal to cos of k power 1 by 2 theta. It is very simple relation. And in the similar fashion, sin k power 1 by 2 into theta plus 2 pi is equal to sin of k power 1 by 2 theta. This is our equation. And to put it differently, after theta has gone through its full range from 0 to pi, the function must join smoothly to its value at theta is equal to 0. Such is the case only if k is equal to n square and n being an integer. Because you should know the value of k. What will be k for different? We are going to sort out cylindrical harmonics, and for harmonics you have some constant and its value being changed after an interval. And what is that interval? That interval is k is equal to n square. Now we return to the second equation. Our second equation was r over by d by dr into r dy by dr. We are able to verify easily that y of r is r power n or r power minus n. Unless n is equal to 0, where y of r is equal to natural log of r, or y of r is equal to constant. Hence, the required solution to Laplace equation, the so-called cylindrical harmonics, will become these three. 1. Rn cos n theta, Rn sin of n theta, natural log r power minus n cos of n theta, r power minus n sin of theta. This is for this part, and this is for the r part. So these are the cylindrical harmonics obtained for the Laplace equation if you consider k is equal to n square. So this was our today's topic. If you have any question, you can ask me, or you can ask the questions after that class via my WhatsApp number. Thank you very much.